So up to last class we have seen about basic mathematics and then vectors and scalars. Okay. So now we will go into the topic, that is measurements and errors. So measurement is nothing but measuring some object. So error is like, suppose we measure any object with n number of time, we will make an object, like we will measure the object with some errors, okay, like 3, 3.1 or 3.2 or 3 like that. Okay, if I take a 5%, if I ask that 5% to measure the object, like the persons will measure different types. Okay, so that's what we are going to see now. So errors in measurement and the least count. So errors in measurement and the least count is nothing but, yeah. So if I consider an object A is there. If I want to measure the object A with a scale which is having a 0 centimeter, 1 centimeter, 2 centimeter, 3 centimeter, 4 centimeter and so on. Okay. So if I want to measure, it lies exactly between 2 and 3. So if I see here which is nearest to that like number, I will say the object is 2 centimeter. Okay. Or else I can say it is 3 centimeter, which is near, I will take that number. So here the counts are like 1, 2, 3, 4 like that. Suppose if I take this scale which is we are using in the day to day life, that is 0, 0.1, 2, 3, 4, 5, 6, 7, 8, 0.9 and then 1 centimeter. Okay. So there are points in between 0 and 1. Similarly in between 1 and 2 the points are like 1.1, 1.2 and so on up to 1.9. Next is 2. So it is up to whatever, infinity. If I take the same object, if I measure I can able to find some number like 2.4. Okay, 2.4. Here the number is 2 centimeter, here the number is 2.4 centimeter. What is the major difference we can find here? Here I can say like approximately 2 centimeter. Here it is near to 2.4 centimeter. If I take the scale like 0 centimeter, 0 centimeter, 0.01 centimeter, 0.02 centimeter up to infinity. In this thing, if I able to measure, I am measuring 2.46. Okay. So whenever I take a least count or a significant value, okay, least count more, I will get a significant values more. Okay. So in this thing, these three things are there, 2, 2.4, 2.46. So which is more accurate value for this? 2.46 is the most accurate value. If I see here only one number is there, second one is 2 number, third one is 3 number. So these numbers are significant numbers, we will say. So 2 is 1 significant, 2.4, 2 and 4 are 2 significant, 2, 4, 6, 3 significant. So whenever I calculate an instrument which is having more significant, that one will have most accurate. Okay. So more significant, more accurate. So this is the point we are coming across in the measurement and errors. Okay. So next one is like, if we measure a length of L is equals to 6.24 centimeter with the help of a vernier caliper. So vernier caliper is nothing but an instrument which is used to measure a object. Okay. Then what is the least count of the vernier caliper, they are asking. So if I consider L is equals to 6.24, so in this least count will be 0.01. Suppose if I consider L is equals to 6.243, so in this least count will be 0.001. Suppose it is 6.2 only, so least count will be 0.1. Okay. Now how many significant figures are there in the measured length? So 1, 2, 3 significant. Which digit are absolutely correct and which is are doubtful? Okay. So if I take 6.2, 6.2, 6.24, 6.246, 6.2463. Okay. These are the values I have measured with the different scales with a different least count. 0.1, 0.01, 0.001, 0.0001 are the least count. So if I see here, which is our like correct values, absolute correct values? For the first one is only 6. For the first one, correct is 6 and wrong is doubtful is 2. For the second one, 6 point and 6 and 2 are correct. Doubtful is 4. For the third one, 6, 2, 4 are correct. Doubtful is 6. For the fourth one, 6, 2, 4, 6 are correct. Doubtful is 3. So when the significant value increases, the last number will be doubtful. Okay, last number will be doubtful and the previous numbers are absolutely correct. So similarly, there is an example which is of length L is equals to 3.267 centimeter. Like if we measure a length of L is equals to 3.267 centimeter with the help of a screw gauge. So screw gauge is also an instrument which is used to measure. So what is the maximum uncertainty or maximum possible error? So uncertainty and maximum possible error are nothing but everything are least count only. Okay, so maximum possible error, uncertainty or least count, whatever they give, everything are same. So what is the least count? 0.001. Yeah, 0.001. What is the significant number? So 4, 1, 2, 3, 4. 4 numbers are available. So 4 significant values. So similarly, like third question is, which are the digits are absolutely correct and which is absolutely like doubtful in this? 3, 2, 6 are correct. So okay. So absolute correct are 3, 2, 6. 7 is for doubtful. Okay. So this is about the starting example for the measurements. Okay. Now we will go and see what is significant figure. Significant figures is nothing but they represent the digit in a numbers. Okay. So whatever we measure now, we will measure in a numbers. So those numbers are significant figures. So whatever now, yeah, whatever we measure we measure in numbers, right? So those numbers are called as significant figures. Okay, understood? No? So whatever the number we are measuring, those numbers are called as significant numbers. Significant figures indicate how preciously a measurement is made. Next is a more significant figure, which has more accurate. So more significant, more accurate, less significant, less accurate. Okay, this is the point you should keep in mind. Okay, now we will see what is the rule to find the significant. The first rule is all non-zero digits are significant. Non-zero digits in the sense except 0, whatever the numbers are available, everything are significant. So for example, if I take 126.28, so as 5 significant. Suppose if I consider 1260. So in this how many significants are there? 3 significant. So 1001, how many significants are there? According to rule number 1. So according to rule number 1, only 2 significants. They are saying that non-zeros are significant. Next we will go for rule number 2. A 0 appearing between 2 non-zero digits are significant. So when I take the example, these 2 examples, no, initially rule number 1 says zeros are not counted. So 1, 2, 3, 3 significant. So here 2 significant. Rule number 2, what they are saying? Zeros between non-zeros are significant. So here in this case it remains as it is. So 3 means 3 only is there. Here we have seen 2 initially for the first rule. Now for the second rule, how many significant? 4 significant. Okay. So rule number 1, rule number 2. Now rule number 3, trailing zeros after decimal places. So trailing zeros after decimal places. Here suppose if I take 1000, 1000 is having any decimal? No, right? So I can say this is one significant figure. So if I consider 1.000, so this is 1.000. Okay, 3 decimal points are there. What is the Third rule, trailing zeros after decimal places are significant. Okay, so I can say here 4 significant. Okay, so similar example is there. L is equal to 6.400 centimeter, which is having 4 significant. So 6 is 1 significant, 4 is 1 significant, the zeros which is after decimal points, so 2 zeros are there, so totally 4 significant. Okay, any doubt in rule number 1, 2, 3? No, right? So yeah, now the significant figure depends on the accuracy of a measurement. Yeah, significant more, accuracy will be more the number of significant, more the accurate the measurement. Okay, suppose if I take the measurement 6.4 centimeter, accuracy is 0.1. Accuracy is nothing but least count. Okay, least count. So the number lies between 6.4 is between 6.3 and 6.5. What about 6.40? 6.39, 6.41. So the accuracy is 0.01 centimeter. So 3 significant values are there. 1, 2, 3. Here 2. What about 6.400? How many significants are there? 4 significant. What is the accuracy? 0.001. The least count is 0.001. What is the number lies between 6.400? It is 6.399 to 6.401. Okay, so it is having 4 significant. So when I consider 6.4, 6.40, 6.400, here the significant values are increasing. It means accuracy also increases. So more significant, like values are increasing, no, here. So here also it will get closer to the number. Okay. Rule number 4. The power of a 10 are not counted as a significant figure. So power of a 10 means like whatever the powers, 10 power 1, 10 power 7, 10 power minus 9, 10 power 10, 10 power minus 100, whatever the powers, everything like power to 10 are not counted as significant. That is rule number 4. Rule number 5, if a measurement is less than 1, measurement is less than 1 in the sense it will be in decimal, 0 point something, okay, 0.0012 like that, okay. Okay, then all 0 occurring to the left of the last non-zero, left of the last non-zero. If I take the example 0.001200, left of the non-zero means to the left. So this is my number, no? This is my number, left side. So are not counted as significant. So then all zeros occurring to the left of the last non-zero, I no need to consider the first non-zero, last non-zero for the left side should be non-significant. Example 0.0042 is there, which is the last non-significant, last non-zero number 4. Before that any zeros are available? Yes, 3 zeros. I should not consider those. So how many significant? Only 2 significant. Okay, suppose if I consider 0.00402, how many significants are there? 3 significant. So this is the last non-zero number. So before that zeros I should not consider. So 3 significant. Okay. Rule number 6. So change in units of a measurement of a quantity does not change the number of significant. So like kilometer, meter, centimeter, millimeter. 1 kilometer equals to 1000 meter. So 1 kilometer equals to how many centimeter? 10 power 5 centimeter. That is into 100, 1000, 100. This is 10. 1 kilometer equals to 10 power 6 millimeter. Okay, so if I write, 1 kilometer will be equals to 1000 meter. 1 kilometer equals to how many centimeter? 10 power 5 centimeter. 1 kilometer is equals to 10 power 6 millimeter. No, 1,000,000 millimeter. Now what is the significant figure for 1 kilometer? one significant figure. What about the 1000 meter significant figure? I can write the 1000 as 1 into 10 power 3, no. So 3, I mean 10 power something, I no need to consider. So how many significant? 1 significant. What about 10, like 1 lakh centimeter? Again 1. So 1 into 10 power 5, which should not be considered, again 1. Here 1 into 10 power 6, so 10 power 6 should not be considered, again 1. So whenever I take conversions, the significant digits are same, it will not change. That is the rule number 6. Rule number 7, here the example, we can write the measurement in other units also without changing the number of significant. 7.2 centimeter as 2 significant, 0.072 meter as 2 significant, 0.000072 kilometer as 2 significant, 7.2 into 10 power 7 nanometer also 2 significant. Okay. Rule number 7 is a terminal or a trailing zeros in a number without a decimal point. Without a decimal point, in the sense we have seen in the starting itself 2000 if I take. So without decimal, so I can write 2000 as 2 into 10 power 3. So exponent should not be considered, so only one significant. So if I take this 2000 as 2.000, how many significant? 4 significant. Okay, that's the meaning of the last rule, rule number 7. So the terminal or a trailing zero in a number without a decimal point are not significant. This sometimes arises due to change of units. Example, 264 meter can be written as 26400 centimeter, 264,000 millimeter. Okay. Yeah. Now the rounding off. Okay, rounding off in the sense, if I consider object, okay, I got the significant figure as 2.638. Okay, how many significant are there? 4 significant. They are asking me to write in 3 significant value. Okay, 3 significant value in the sense I need to consider only starting 3. The ending one should not be considered, but there are some rules to consider those also. Okay, the first rule is if the number lying immediately to the right of a cutoff digit is less than 5. Okay, here I will say the example. Here the last digit is less than 5 or greater than 5? Greater than 5. So what I should do is, the previous number is there, no? 3 is there, no? I will write here. Object is there, object A, I have measured it as 2.328. Okay, write this as 3 significant. So the last number I should see. If it is greater than 5, previous number should be added by 1, which means 2.33. Suppose if I take the same number, but the last number is 2.324. Okay, number is less than 5, no? Less than 5 in the sense, no need to do anything, write as it is, 3.232, 2.32, that's it. So rule number 1 is if the number lying immediately to the right of the cutoff digit. So cutoff digit in the sense I am cutting this digit. Okay, cutting and adding zeros, that's it. Okay, is less than 5, then the cutoff digit remain unchanged. So it remains unchanged. That is the rule number 1. Rule number 2, if the number immediately to the right of a cutoff digit is more than 5, so then increase the cutoff digit by 1. So I have increased by 1. Understood? Any doubt here? So the examples, here it is 6.35 I have given. Okay, it is equal to 5. Now what I need to do? Okay, we have seen less than 5. Okay, greater than 5, everything we have seen, less than and greater than. Now if they are asking equal to 5. Okay. Yeah. Rule number 3. If the number to be dropped is exactly 5 followed only by the zeros. Okay. If the cutoff digit is even, it remains unchanged. If the cutoff digit is odd, increase by 1. Now listen. First two rules understood, no? Greater than 5 means previous number increased by 1. Less than 5 means previous number remains unchanged. Now the number is 6.325. One more number is 6.335. Okay, last numbers are equal to 5. What I should check is previous number is either even or odd, I need to check. Okay, if it is even, leave as it is. So answer will be 6.32. That's it. If it is odd, no, what I need to do? I need to change this as even. So plus 1. What is the answer? 6.34. Okay. So 5 is there. Previous number, if it is even, leave as it is. Previous number is odd, I need to add 1, that is 6.34. Any doubt in rounding off now? So 3 rules: less than 5, greater than 5, equal to 5. For equal to 5, previous number even, leave as it is. Previous number odd, I need to add 1. Okay. Yeah. Now algebraic operation with significant. So now we have seen that significant figures. Okay. Suppose I am taking object, like 3 objects I have taken. So 3 objects having 3 different significant. Now they are asking to add the significance. Okay. So example 1.2, 3.45, 6.789. If I add, I am getting 11.439. So the rules are, when adding or subtracting measured value, the least number of a digit after the decimal among the numbers determines the decimal places. Keep in mind, whenever you are doing addition or subtraction, okay, like algebraic operation means addition, subtraction, multiplication, division. Okay. So for addition and subtraction, keep in mind least decimal point. Okay, least decimal point. I will add here addition and subtraction. Addition and subtraction, multiplication and division. So for this I need to consider least decimal. Least decimal. Okay. For this, least significant. Okay. For addition, subtraction, least decimal, multiplication and division, least significant. Now come to the problem. For the first example, 1.2, no, 1.2, 3.45, then 6.789. If I add everything, I am getting 11.439. First one, how many significant? 1.2, 2 significant. Third one, sorry, second one is 3. Third one is 4. This also having 4 significant. These are the significant numbers. Okay. Now, if you see which is having least decimal, 1.2 is the least decimal. No. Now, the answer is there. No. 11.439. Okay. 11.439. First decimal, only one decimal I need to consider. For addition, I have said no, need to consider the least decimal. So which is having, this having 1 decimal, 2 decimal, 3 decimal. I need to consider least decimal, that is 1. Okay. Now round off to only 1. 11.4. Okay. Keep 11.4 as it is, but try to check the next number. If next number is less than 5, I can write 11.4 as it is. If it is greater than 5, 11.5. If it is equal to 5, the previous number is even, no need to change. Understood? This is the example 1. Example 2 is there. Example 2 is 12.63 minus 10.2. We got the answer as 2.43. How many significant for this? 4 significant. For this, 3 significant. But the decimals are, if you see, 1, which is having least 1. So I need to consider only 1. So 2.4 I can consider. The next number is 3, which is less than 5. So I can write as it is, no, 2.4. Any doubt here? Rounding off for addition and subtraction. Now for the multiplication. Okay. Multiplication and division, what I need to consider? Least significant. Okay. Now if I multiply the 1.2 into 36.72. Okay. How many significant? How many significant? What is the answer I got? 44.04, sorry, 064. How many significant? 5 significant. These 2, if I multiply, this is 2 significant, this is 4 significant. I need to consider only least significant. So this is 44.064. No, 44.064. I need to consider only the 2 significant. Next significant is 0. No need to worry about anything. So I can write 44, which is nothing but I can, if option is 44, I can, but if they are giving 44000, this is also correct, because 44,000 no can be written as 44 into 10 power 3, which is no significant for this. This is too significant. Okay. Any doubt here for addition, subtraction, multiplication and division? Okay. Can you give answer for these questions? Guys who are watching in online, no, you can give the answer in the comment boxes. We'll check it. So if you have calculator, you can use it and you can give the answer.
First one is 261.1.
261. 261.1. That's the answer. Correct answer. Check it once. 13.214 plus 234.6 plus 7.0350 plus 6.38. 261.2. Okay. Now, which is having the least decimal points among the first one? The addition, no. I need to check least decimal. So, first one having
3 decimal points.
3 decimal points. 1 decimal point, 4 decimal points, 2 decimal point. Now what I should do?
261.2.
That's the answer. Okay. Answer is only this one. It will be extra, no, like it will be 261.1490. Okay. This is the answer you are getting, right? But if you, this is the versional answer. You need to check the versional answer now. How many like significant, I mean how many decimal I can consider? 261.229. Okay. Okay, fine. Now, how many decimal I can consider?
Only
one decimal only. Least decimal. One decimal I can consider. The next point is less than 5. No. So, no need to do anything. It is 261.2. That's it. What about the second one? No, total answer. 1909.5. That's it. Okay. How many decimals are there? 0 decimal, 0 decimal, 0 decimal. I mean this 1, this 0. Least decimals are 0. Now what I can do now?
It is
Equal to 5.
I have to get the
Previous number.
If it is odd, I have to
Increase it by 1. What will be the answer?
1910.
That's the answer. That's it. Okay. Now what about the multiplication? Simplify and round off to the appropriate number of a significant digit. 16.235 into 0.217 into 5. I have given the long number now.
17.61497.
Yeah. 17.614975. Okay. How many significant? Least significant I need to consider, no? How many significant? 5, 3, 1. So what will be the answer here now? Least significant should be 1. First number I can consider. The next number is more than 5. What I should do? Increase it by 1. Okay. 2, 0. That's it. Answer it, that's it. Points are there. But what they are asking? They are asking multiplication, no? Least significant. So 20 is the answer, that's it. 614975. Okay, suppose I am getting 179.5. The least number is, least significant is 1. How many, how can I round off this one?
We have to check on the 7 and 9.
Only one I can keep as it is, 7 I should check. 7 is greater than 5. So what will be the answer? 200, which is nothing but 2 into 10 power 2. So 200 is near to 179.5. Again 20 is near to 17.614975. Right, that's the answer. What about the second one? Understood, no?
Yes, sir.
Yeah. What is the second one answer? 0.00435 into 4.6. What is the answer you got? 0.02 001. How many significant? 2. How many significant? 3. What is the least significant? 2 significant. So this one no significant. If I see this is the significant, no. So 2 significant. So next number is 0. No need to consider anything. Now what I can do? 0.020. That's it. That's the answer. Any doubt now? Any doubt in this? Okay. Next is permissible error. So permissible error is the maximum allowable error in the measurement which is acceptable for the particular instruments or measuring device being used. So it is also called as least count. So we have seen the least count now. The other name of least count is permissible error. Okay. Or the smallest error that can occur due to the limitations. So due to limitations in the sense, like if I consider the vernier caliper or anything, the least count will be 0.1 centimeter. Okay. So this is the allowable error for that. Okay. This much error only can used for the instruments. Okay. So smallest error that can occur due to the limitations of the instrument precision. Okay. Example, if we measure a length of L is equal to 26 millimeter. Okay. Then the maximum value of the true value may be 26 plus 1 can be 26 minus 1 also can be. Yes or no? It lies between 25 and 27. That's the thing we have seen here in the table. Yeah, in this table we have seen, no, 6.4. It can lies between 6.3, 6.5. Okay. Similarly, 6.40 can be 6.39 and 6.41. Okay. So 2. So what I can say, 6.4 can be written as 6.4 plus or minus 0.1. No, this is my least count. No, so least count should be written. Similarly, for 6.40, how can I write? 6.40 plus or minus 0.01. This is my least count. It can be either 639 or 41. Okay. Again, 6.400 is there. How can I say? 6.400 plus or minus 0.001. Either it can be 6.399 or 6.401. That's the meaning of the least count. Okay. Yeah. Understood. So it can be 27 millimeter or it can be 25 millimeter. The true value will be lies between these two. Okay, only these two. It won't come more than 27, it will not come less than 25. Now the classification of errors. Okay, errors can be classified into two classes. First class is systematic error, random error. Okay. Second one is absolute, mean absolute and relative. So relative in the sense I am relating two things. No, two things if I relate I can say the fraction also. No, like division. No, numerator by denominator. If I relate anything I can say it's fraction also. Okay. So first we will see what is systematic error. So systematic error are the error whose causes are known to us. Okay. If I measure measure a person's weight, like if I go to gym, if I measure my weight, it will be shown some x value. If I come to home, if I measure the weight, it will show some y value. I can say like it has been varied. I can see visually. But for the random error, no, the second topic, I will complete this one. So which known to us. Such error can therefore be minimized. I can minimize that error. How I can minimize means I will take n number of times. If I consider 5 times I measure, So if I measure 5 times, for example 70, and for second time I am getting 71, for the third time I am getting 71.5, again fourth time 70, fifth time 71. Okay, these are the values I have measured in both machines. Okay, now I can take the average value. If I take the average value, I can get the precision value, right? That's how I can minimize it, the systematic values. Okay. So instrumental error due to enormous instrument can be reduced by using more accurate instruments. If I take a scale, 1 centimeter scale, if I want to measure the board, okay, it can measure up to 40 centimeter or 50 centimeter, like approximately. If I take 0.1 centimeter, no, I can measure somewhat accurate. Again, if I take 0.01 centimeter, I can measure more accurate. If I increase the least count value, I can increase the accuracy. That's the thing first point says. Second point, errors due to neglection certain facts. Example, ignoring air resistance in pendulum experiment. If I take a pendulum, no, in vacuum if I do, I will get some exact thing. But if I do in air, no, air resistance will takes place there. Okay. The third one is errors due to environmental condition like temperature, pressure and humidity. Okay. These can be neglected by seeing, like visually we can see. Okay. Next one is random error. Like cause of random error are not known to us. That's the meaning of random, like it's occurring randomly. Okay. It is not possible to remove them completely. They may arise due to the variety of reason. Example, sensitive balance reading disturbed by the vibration of the vehicle nearby. Okay. So random error can be minimized by repeating the observation. That's what I said. If I repeat the observation, I can get the some precision value. If I take the same thing, no, 71, 71.5, 70, 71, 71.5. So how many times? 5 times. If I add everything, divide by 5, I will get some approximate value. Okay. That is the meaning of mean. Okay. Mean value will say. Okay. Now the absolute error. So absolute error is nothing but like this is mean error. Okay. Mean value. Now absolute error. The difference between the true value. What is the meaning of true value? The one we measured actually, and measured value. Measured value in the sense? The given value. Okay. Of the quantity is called the absolute error. The difference means subtracting. So usually the mean value, that is AM, is taken as the true value. Okay. This is the true value. That's the thing we have seen. No. This is true value, and whatever we have seen here, this is measured value. Okay. Yeah. Now I have taken the true value here. Okay. That's the formula for the true value, or we can say either mean value or true value. Now if I want to find the error for each cases, so I saw, like I took 71, 71.5, 72, 71, 71.5. Okay. Can you find what is the true value for this? True value is A mean is equals to 71.4. Okay. So now if I see 71.4 and 71, what is the error has been made by the measurement? 0.4. So how can I say, like true value minus the absolute, like that is the value which we have measured. Okay. So the true value is how much? 71.4. What is the value we measured? 71 minus 71. What is the answer? 0.4. That's the error for the first number. For the second number, 71.4 minus 71.5, it is minus 0.1. Okay. Again 71.4 minus 72. 72 only, no? So 0.6. Again 71, no? 71.4 minus 71, it is nothing but 0.4. Again 72, right? Or 71.5. Okay. 71.4 minus 71.5. How much? Minus 0.1. So these are the absolute error made by the object or like measurement. Okay. Now mean absolute. We have seen the absolute error. No, what is the meaning of again mean? Adding everything and divide by the total number. Now what are the number we got? 0.4, 0.1, 0.6, 0.4, 0.1. So whatever it is, negative or positive, consider everything as positive only. Okay. 0.4, 0.6, 0.1, 0.4, 0.1. Divide by 5. So 0.4 plus 0.6, 1. 1 only, no? 1.1, 1.5, 1.6. So 1.6 divided by 5. What is the answer? 1, 2, 1.2, 3.2, 3.2, no? 0.32, 0.32 answer. Okay, this is the mean absolute error. Okay, mean absolute error. Now, this is the least count, like we have considered, no? 0.001, yes or no, plus or minus 0.01, 0.001. Now, what is the A mean we got? A mean 71.4. So this is the A mean, like some accurate value, that is 71.4. What is the error accurate we got?
0.32.
Plus or minus 0.32. That's it. That's the answer of the question. Okay, we have measured the values. How much errors it has been made, I need to find. So errors I have found out, like each one having each error, but the absolute, like mean absolute also I need to find. Okay, so mean I have found for the values, like whatever value we measured. Again we need to find what is the error made by that. So I need to take the error and I need to take the mean error. So 71.4 is the mean, 0.32 is the mean absolute error. Okay, so that's the like final result. Final result can be written A is equals to AM plus or minus delta A min. Okay, so we can write the value AM plus delta AM or AM minus delta AM. Okay, that's the meaning of the question. Now if they are asking about the relative, no, so relative in the sense, what is the answer? 0.32, no, 0.32, 71.4. Okay, so if I multiply with 100, no, I will get percentage. If I do only this, I will get the relative. What is the relative error? 0.32 divided by 71.4, 0.0044. This is my relative error. If I want percentage, no, multiply by 100, how much? 0.44 percentage. 0.44 percentage is the error. That's it. Yeah, understood? Any doubt in this? So the first formula, what I need to do? We need to add all this thing, divide by the total number of the value, and then what I should do? Yeah, I need to find the mean error. Before that I need to find the errors of the each one value. Next is mean error, divide by the total number. Okay, next is to find, like if they are asking about the result, I can write A mean plus mean absolute. Okay, mean absolute. So if they are asking relative, absolute, like mean absolute error by A mean. Okay, average I can. So percentage in the sense into 100. That's it. Any doubt here? Okay. So we will see one more topic. Now the combination of errors. Okay, suppose like for previously what we got, 71.4 plus or minus 0.32. This is one value. Okay, second one they have given us 73.8 plus or minus 0.43. Okay, they are asking me to add A plus B or subtract A minus B. Okay, so the formula is simple. A plus B in the sense, add this and this 71.4 and 73.8 and this two. What is the answer? 71.4 plus 73.8. What is the answer? 144.2. 2 plus or minus. What is 0.32 plus 0.43? 0.75. Okay. So that's for the addition. For subtraction, no? Subtraction. These two I need to subtract it. What is the answer? Minus 2.4. Minus 2.4. But for the errors, no, I need to add as it is 0.75. Addition, add everything and add the errors. Subtraction, subtract this one and add the errors. For errors, I need to add first both subtraction and addition. For addition, I need to add both of them. Subtraction, I need to subtract both of them. Okay, I'll give one example here. You can solve this one. Okay, the volume of two bodies are measured. V1 is equals to 10.2 plus or minus 0.02 centimeter. V2 is equals to 6.4 plus or minus 0.01 centimeter cube. Calculate sum and difference in the volume.
16.6.
So first one, V1 plus V2, no. What I should do? I should add both of them. 10.2 plus 6.4? 16.6 plus or minus 0.02 plus or minus 0.01. How much? 0.03. What about V1 minus V2? 10.2 minus 6.4? We'll get 4. 3.6. 3.8. Check it. 3.8 will come, I guess. 3.8, yeah. So 3.8 plus or minus 0.03. And I should add the errors. Okay. Any doubt here? So we'll continue with the multiplication and division in the next class. Okay.